Okay, so first of all, welcome all to this, which is the fourth episode of the second season of the O+Ne+Mg series of seminars. Today we are going to have a talk by Dao Hai Li from Beijing Normal University about how tidally disrupted asteroids pollute white dwarfs, and another talk by Daiichi Hiramatsu from Harvard Smithsonian, who is going to talk about the Center for Astrophysics, who is going to talk about the electron capture origin of supernova 2018 ZD. So in principle, I think we are going to start with Daiichi, if you are okay with that.
Yeah, I'm fine with that.
Okay. So I think that we can start now, if you want to share your screen. And so we have 20-minute talk. Do you want me to tell you a couple of minutes before that?
Like, yeah, if you can give me heads up like 3 minutes before.
Okay, perfect.
That'd be great.
I will do that. Okay. Please go on.
Do you see the presenter mode, or are you seeing the?
No, I'm seeing the presentation mode.
Only the presentation mode. Let's see.
No, this is okay, I think, huh?
You're only just seeing the slides, not
yeah. Oh, yeah, the slides. I'm seeing the slides, so please.
Okay, so that's cool. All right, so yeah, thanks Marcel for the introduction, and then thanks for having me for today. I'm Daiichi Hiramatsu, a new postdoc at the CFA at Harvard and Smithsonian. I did my graduate work at Laskin Universal Observatory, and then today's talk is mainly from that work, and then which is on the electron-capture supernova 2018 ZD. So for the talk, I'm gonna introduce an electron-capture supernova. So what is an electron-capture supernova? And then I'm gonna briefly talk about Laskin Universal Observatory and then the Global Supernova Project, where we got the data from. And then discuss this 18ZD, which you can see here as a best candidate for the electron-capture supernova. All right. So I'm going to start with the introduction, and then so this is a massive stellar evolution in one plot. So it's a busy plot, but there are two relatively well understood regimes in massive star evolution. One is that for the low mass stars below about 7 solar masses or so, they become red giant and then die as planetary nebular, leaving CO or oxygen neon white dwarfs. And then if it's CO white dwarf, they might end up as a type 1A supernova if they have a binary companion. And then for the massive star regime, about 10 or 11 solar masses, they become red supergiant, forming an iron core, and then they die as iron core collapse supernovae, leaving neutron stars or black holes. So those are the relatively well understood regimes in stellar mass evolution. But what's in between here, about 7 to 11 solar masses, the evolutionary path is really complicated because of the mass laws, and other mechanisms. But what we think is that they become super-asymptotic giant branch star here, SAGB stars with the degenerate oxygen neon core. But depending on the Maslow's prescriptions, and convection and others, they might die as just white dwarfs, so they might explode the thermonuclear explosion or electron capture supernova. So as I said, the complicated evolution results in diverse outcomes, from CO white dwarfs to oxygen neon white dwarfs to even to electron capture supernovae. But the identification of electron capture supernovae and their SAGB progenitors still remains elusive. So that's a big question. And then, so what is the stellar evolution? What is explosion physics? What's the remnant populations, what's nucleosynthesis, and what's chemical evolution? So this is those are the big questions that really depends on this mass regime. So for their explosion mechanisms, unlike iron core collapse supernova, where you have iron core, the progenitors for the electron capture supernova is a super-asymptotic giant branch star, SAGB star. That is the end state of stars in the mass range of around 8 to 10 solar masses. And their core is composed of a degenerate oxygen, neon, magnesium, which is pressure supported by the degenerate electrons. But when the core becomes dense enough, 20 neon and 24 magnesium start to eat up electrons. So that's so-called electron capture reactions. And then since the core is supported by the electrons, this reduces the core degenerate pressure and then induces a core collapse supernova explosion. So this is the explosion mechanisms for electron capture supernovae. And so what's their observation? What are their observational signatures? On the left image, you see the ALMA radio image of just the asymptotic giant branch star, not super. So it's a slightly lower mass asymptotic giant branch star, but still you see like really complex circumstellar material surrounding the progenitor star, surrounding the AGB star. So you'd expect for super-asymptotic giant branch star, you'd expect even more than circumstellar material. And then also from the star structure, you'd expect large progenitor radius of about 1,000 solar radii. And then you'd also expect low ejector mass compared to iron core collapse supernovae because the progenitor mass is smaller. And then also the low explosion energy because of the explosion mechanisms. And then also the low radioactive nickel yield of about 0.01 solar masses. Sorry, less than 0.01 solar masses, which is about an order of magnitude smaller compared to the typical iron core collapse supernovae. And then also high stable nickel 58 yield. So electron capture supernovae are expected to produce more stable nickel than radioactive nickel, which is different from iron core collapse supernovae. So this was first theorized like 40 years ago, but no definitive observational identification yet. So that's a big remaining question. And so then I'm going to briefly talk about the Laskin Universal Observatory, where we got the most of the data from. So it's a global network of 25 robotic telescopes all over the world, so we can react any transits at any moment, at anywhere in the sky. So that's the idea. And then the Global Supernova Project is a key project at the Laskin Universal Observatory, where more than 150 astronomers with more than 3,000 hours of Laskin Universal Observatory time to follow more than 150 supernovae per year. And then this project is a global collaboration, so it's also complemented with the world's largest ground and space-based telescopes such as Keck, Gemini, Swift, and HS2. So this is how the scheduler looks like for Laskin Universal Observatory. So everything is robotic. So the schedule itself is robotic, and then what we do is just request an observations, and then scheduler, makes that. I mean, the scheduler literally makes the schedule based on the priority. So you see on the left, you see the sites. So this Siding Spring is in Australia, and then we have 40 centimeter telescopes, 2 meter telescope, 1 meter telescopes, and same for the different sites. And then you see, like, what observations are planned and what not. So this is how we manage the observation, how we manage the schedule. And then for the supernova, we have this really nice page called SNETS, which is written by the former postdoc at Yaya Arkabi, who is now at Tel Aviv. And this is like a Facebook page for, a supernova. So you see like, comments, people saying why this is interesting. And then here you can also see the data. So on the bottom left, you see photometry, what the light curve looks like. And then on the bottom right here, you see the spectra. So this is, as I said, it's like a Facebook page for supernova. And then we have a unique page for each object that we are following. And then to make observations, you just go to the scheduling form, and then you see, you define, you just give exposure times depending on the brightness of the object, and then set the cadence and other parameters, and then you just submit it. And same for the spectroscopy observations. So this is like a, you have all this power, and then you can, just do this on your smartphone. So that's a really cool part of it. And then this is a really complicated plot, but to study supernova from different angles, you really have to have these, many data sets, like, pre-explosion images, RE light cards, light spectra, well sample spectra, or blah, 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 blah. And then each connects to different supernova properties. So like, we use HST, Swift, Keck, Gemini, and then my part is to like, get those observations. And then also I do some, like modeling. So compare these observations to the model to extract as much progenitor properties as possible. So that's the goal of this project. And now I'm going to talk about the supernova 2018 ZD, which we claim as the best yet electron capture supernova candidate. So it was discovered by a Japanese amateur astronomer Koichi Takaki, and then it was discovered on March 1st, 2018, just merely 3 hours after the explosion. And then this was my mom's 60th birthday, so that was, that was something. And then if you look at the HST archival image, you see a faint candidate here. It's really like, faint, but compared to the supernova image, which was taken in 2019, the position is like, consistent with the supernova position. So we identified this as the progenitor. And then for the LCR and GSP, we started observations right after the discovery. So just like, just 14 hours the discovery announcement, we started our observations. So you see, so sorry, 14 hours from the announcement. So there was a discovery point announcement and then our first LCO data point here. So we started follow-up like just right after the announcement. And then these area observations revealed like, blue word early color evolution. So if you just look at this inset, which compares to the Swift UBWT minus B colors. So compared to like, other typical core club supernovae, which just becomes, bluer because they're getting colder, because they're getting cooler. But for 18ZD, which is these black points, shows this like, a dip. So it shows RE blue word evolution and then becomes red. So there has to be something surrounding the progenitors to cause this like, really interesting light UV color evolution. And then if we compare this to the models, which are these lines color coded by the mass loss rate. So this is 10 to minus 1 solar masses per year, 10 to minus 3 times 10 to minus, sorry, 3 times 10 to minus 1, 10 to minus 1, 3 times 10 to minus 2, and then this is 10 to minus 2 solar masses per year. So to reproduce this, early blue white color evolution, you have to have really dense CSM, which we estimated as 10 to minus 2 solar masses per year, assuming a wind-like CSM. So it has to be a really dense circumstellar material to cause this early blue white color evolution. And then we also saw this so-called flash features. So this is comparing 18ZD in black with other, supernovae with flash features. And then these flash features are these narrow, like, hydrogen, helium, and carbon lines, which comes from the circumstellar material that is flash ionized by the shock breakout radiation. So supernovae, some of the core supernovae show these flash features early on the evolution, but but it disappears once the SN ejector overruns the CSM. So, but for the 18ZD, we are seeing this really persistent flash features that, like, disappears around 9 days after the exposure. So this is really like, long compared to typical 3 to 5 days to typical island core club supernovae. So combining these early blue white color evolution, these flash features, we infer really dense circumstellar material. And then we also kept like, photometric observations until 400 days after the explosion. So this is showing the light curves, colored by the filters. And then you see like, these really typical type 2 supernova light curve shape where this part, which almost like a plateau, is powered by the hydrogen-rich envelope. But once the photospheres recedes to the base of the hydrogen-rich envelope, it shows the drop in the light curve, and then it stays on the what we call as the light curve tail, which is now mainly powered by the radioactive decay of 56 cobalt. And so this long-term photometric follow-up revealed this large plateau drop So compared to a sample of type 2 supernovae, the other typical iron core club supernovae, it shows the largest drop from the plateau, which indicates that there is a really low radioactive nickel yield because the, radioactive nickel 56 decays to radioactive 56 cobalt, and then that cobalt decays into iron, and then this part at this time it's powered by 56 cobalt, so the low mass of 56 cobalt corresponds to raw mass of 56 nickel produced in the explosion. So this large light gap drop shows really low radioactive nickel yield, also low explosion energies, and then low ejector mass and large radius with some light gap degeneracy. And then we also kept spectroscopic follow-up for until 600 days after the explosion. So this shows the spectrum series with our LCO GSP follow-up, which started right after the explosion to 600 days after the explosion. And what's interesting here is that in this region, you see a really strong Rhine ratio of nickel 2 to iron 2. So nickel 2 is this blue shaded region here, and then iron 2 is this pink shaded region. So if you take the Rhine ratio of this, you really see the nickel 2 is stronger. And then here, nickel 2 comes from stable nickel, because all the radioactive nickel should have decayed into iron 2 at this late phase. So this Rhine ratio gives a rough estimate of the production, ratio of radioactive nickel to stable nickel. And then the fact that we see stronger nickel 2 line here compared to iron 2 line tells you there was a more stable nickel yield in the explosion. So these are the observations that led us to, claim this is the best yet electron capture supernova candidate. So as I said, going back to the checklist of the electron capture supernovae that they show, then circumstellar material, and then also large progenitor radius and low ejector mass. I put question mark here because there's some uncertainty because of the light gap degeneracy. But also low exposure energy, radioactive nickel 56 yield, and then also the high stable nickel 50 yield. So this looks like, all the observed features are consistent with electron capture supernova. So that's why we claim that this is likely the best yet electron capture supernova candidate at the moment. And then based on these observations, we put a really rough estimate on the electron capture supernova rate. So on the bottom panel, on the bottom x-axis, it's the electron capture supernova rate estimate with respect to the all core club supernovae. And then here, it's showing the delta MSHB, which is the mass window of the SAGB stars that can end up as electron capture supernova. So in this regime, we estimated the electron capture supernova rate of 1 to 9% of all core club supernovae, which corresponds to about so, and then this this finding, and then also the this rough rate estimate is interesting because it has many implications for the stellar evolution and then supernova physics. So for the stellar evolution, it has progenitor mass window. Based on this rate estimate, we can say it's about 0.06 to 0.69 solar masses. So that's the mass window for the SAGB stars. And then also for the core collapse physics, that the electron capture rates. So there's a battle between electron capture rates and the oxygen flame speed. But the fact that we can see the electron capture supernova tells you that the electron capture rate is higher.
3 minutes.
And then, all right, thanks. And then for nucleosynthesis, it's, since it has different nucleosynthetic yields from, typical iron core club supernovae, it has an implication for the galactic chemical evolution. And then also the neutron star mass distribution, because we expect the electron capture supernova to leave low mass neutron stars, which might correspond to the low mass peak in the neutron star mass distribution. And then also for the gravitational wave source population, because electron capture supernova has really small kicks, so the what's left has really low eccentricity, so it's easier to merge within the Hubble time. So these are, this finding itself is interesting, and then it has many implications to the, many fields of astrophysics. So yeah, that's it for my talk. Thank you for listening, and I'll take any questions.
Okay, thank you very much for your presentation. Very, very interesting, really. So let's see if there are some questions from the public. I don't see in the chat, there are none. So is anyone? So other questions? Or
Yeah, can I ask a question?
yes, please go on.
The progenitor that you saw in the HST image, you said that the radius is not right, or is? Can you elaborate on that, please?
Oh yeah. So from the progenitor identification, we can only say there's a faint progenitor because there was only a single band detection in the pre-exposure images. So we cannot say too much about the radius. We can only say that brightness is consistent with what we expect for the SAGB stars.
Okay, because you have only one band, so you can't say what the color is, so you can't estimate the temperature.
Right, you're right.
But can you, from the non-detections, you can maybe put some limits or not useful limits?
Oh yeah, so let's see if I can. So here is the, some limits. So we have also limits at the, slightly bluer band here, which might be constraining. And then this is the detection. And then it's compelling with, so this, this red data points is a galactic SAGB candidate.
Mm-hmm.
And then looks like it's more consistent there compared to the, some red supergiant progenitor models plotted in dotted lines. So that's pretty much all we can say. So we cannot really say about the temperature or the size.
Mm-hmm. Thank you.
Okay, so I think we have another question here. So there's a question by Boris Gansike. Can you make predictions on the number of massive white dwarfs resulting from this channel of core collapse supernovae? I'm not so sure. I mean, these objects end up in neutron stars. So
yes,
but in principle, there is one thing which is true, is the fact that those that go to the supernovae, the super-HEV and do not end up in this channel will end up as oxygen neon white dwarf. That's true. So in principle, the fact that you find a very this is a bit of a question of myself and a comment. So you find a very small window, mass window for the progenitors of this scenario. Am I right? Because it's
right.
That means that the vast majority of super-HEV stars will end up as oxygen neon white dwarfs, which is quite interesting.
Yeah, it's likely the case, but this is just one, identification. So, what we are hoping to do is to do more statistical analysis on the large homogeneous sample. That way we can get more constraint rate estimates. And then that would constrain the, projectile mass window better.
Because in principle, with the mass window that you found, is I would say the vast majority of super-HEV stars will end up as oxygen neon white dwarfs, which is interesting in itself. Okay, so we still have time. So are there more questions? Otherwise, I would ask. There is a question here by Maria. So she asked, what are the implications for the mass range? Oh, okay, so I think this is the same question that we already discussed.
Yeah.
What is the implications for the super-HEV stars that will end up as oxygen neon white dwarfs, which is the same thing. So I think we still have time. So I will. Can you tell again discuss again the observational evidence for the nickel yields, because I missed that a bit.
Sorry, can you repeat your question?
So can you discuss again how the observational evidence for the nickel yields that you mentioned?
Okay. Yeah, so here we are seeing this plot here, and then just looking at this left part here, and then for this blue shaded region is the nickel 2 line, and then this pink shaded region is the iron 2 line. Okay, and then this was taken like after 300 days to 600 days after the explosion. So at this late time, all the radioactive nickel should have decayed into iron.
Okay.
So what we see here is the iron 2, mainly from the radioactive nickel 56, decayed into iron at this phase versus the stable nickel produced in the explosion. So this Rhine ratio, like roughly gives us an estimate of the stable nickel yield to radioactive nickel yield.
Perfect. Okay, now I understand. That was what I missed. Thank you very much.
And then I see one more hand by Alexei.
Okay, yep, please go on. I don't see it.
Great. Well, thank you. It was a very interesting talk and a very interesting system as well. So I was wondering about the CSM interaction signatures in the beginning. So you were considering the models with mass loss from the super-AGB star. And I mean, how possible it is that it's not an outflow, but more like a hazy mass cloud sort of present around the star? So I mean, like in other words, if you assume that it's an outflow, you then automatically assume that the CSM has a functions like 1/r² decay. So, and if you assume that it's a cloud, it could maybe be different structure. So could that help explain anything?
Yeah, that's an interesting question. So for this analysis, we just assume it's a wind-like CSM, but like, even if you assume an outburst or something, you still have to have this high much mass to like, show this, really early blue white color evolution. So I think that regardless of the, CSM structures, I think there has to be a certainly high CSM mass. And then that's what's important here. So, but this, mass loss rate is, is based on our wind-like CSM assumption. So that's a good question.
So just the thought that this might be a bit easier to arrange having a cloud of 0.01 solar masses around than having a constant mass loss rate of 0.01 solar masses per year. Well, just
yeah, right. But either way, it has to have a lot of CSM just